So this is a nice and easy lab. I know we just had our exam, so this is a nice break. This lab will be due at the end of the week after spring break. So there's no expectation that you work on this lab during spring break, but I'm introducing this lab ahead of time. So that way, if you want to, you can. Okay, so this is lab 28, which is the bromination of acetanilide. And of course, we've seen acetanilide before. We've actually made it in lab 23. So in this case, we're brominating acetanilide with excess bromine HBr and acetic acid, and we exclusively get the para-bromo or 4-bromo acetanilide product. Now, in terms of the mechanism, oops, there was a small error in the cut and paste tool. So in terms of the mechanism, we know that this amide is a pi donor, so it's an ortho-para director. But because it's very hindered, we see exclusive direction to the para position because the ortho positions are too hindered and they're blocked by our amide group. So per any electrophilic bromination mechanism, our nucleophilic pi bond attacks our electrophilic bromine atom, and then we eliminate a proton, we eliminate a hydrogen atom to regenerate our aromatic system. One thing that's a little bit interesting is because our aromatic ring is so activated by our amine, we can just use bromine rather than having to resort to using an additional catalyst like iron tribromide. Once we get our para-bromo acetanilide product, we're going to quench our reaction mixture with sodium hydrogen sulfite. That just gets rid of the excess bromine because you don't want to be handling bromine outside the fume hood. We are going to isolate our product via filtration and then rinse our product with water. To answer the question, why don't we need to use a catalyst? The reason why we don't need to use a catalyst is because our aromatic ring is already activated by a very strong pi donor. So when you have these activated aromatic rings with pi donating groups and electron donating groups, you don't necessarily need to use a catalyst. So once we isolate our para-bromo acetanilide via filtration, we'll be able to weigh and record the mass of our product. From there, we're going to characterize our product via IR, proton NMR, carbon NMR, and melting point. And the beautiful thing is you should already have the spectral data for acetanilide from your last report, right? So you only need to find the spectral data for the product. And conveniently enough, your lab manual has the proton and carbon spectra. So if you cite your lab manual for your spectra section, that'll be more than okay. We're then going to be doing some chemical tests, the same chemical tests done as in experiment 23. We won't be doing TLC. The IR, NMR, carbon NMR, and melting point are more than definitive enough for characterization. And this reaction is functionally quantitative, so we don't really see the TLC, you just see one spot and then the product would have a different RF. I felt it was a little redundant considering how extensively we characterize this compound using other methods. You can exclude the TLC procedure in your procedure section, as we don't actually do it in the recording. In terms of chemical tests, we're doing the hydroxamate test for esters and amines. So treatment of our amide with hydroxylamine generates our hydroxamate, which upon treatment with iron trichloride generates a red complex, which serves as a positive test and a positive confirmation of an amide or ester. Does this make sense to everyone? Does this look familiar? The other tests we're going to be doing are the ignition test, which detects the presence of an aromatic ring, and the soda lime test, which detects the presence of a nitrogen functionality. The new tests that we're doing are the silver nitrate test, which detects an alkyl halide. If you see a solid precipitate, that's a sign you've made silver chloride. And the Beilstein test, which serves as a general test for halogen functionalities. If you want more information on these tests, I would look at experiment 2B, as we've actually done these tests in previous labs. Now you may say, why are we doing two tests for a halogen? The silver nitrate test looks for an alkyl halide, while the Beilstein test is more general and detects any halogen functionality, including aryl halides. So on that note, would you expect the silver nitrate test to give a positive result? Would we expect the silver nitrate test, which detects alkyl halides, to give a positive result? So if we have parabromo acetanilide, this is an sp2 carbon, it doesn't engage in displacement reactions, and thus the silver nitrate test would likely not give a positive result. Aryl halides generally don't give positive results for the silver nitrate test. The Beilstein test would give a positive result. Does that make sense? Okay, for our last set of characterization, we're going to be repeating the solubility tests done in experiment 23A. So we're going to be looking at the solubility of our product in water, sodium hydroxide, hydrochloric acid, sulfuric acid, and phosphoric acid. These solubility tests, if we still have our amide, would ideally give the same results. So we're going to interpret both the spectral data, chemical test data, and solubility test data, and we'll be able to conclude whether or not we've made our desired parabromoacetanilide product. And again, I would emphasize that a lot of the spectral data is in your lab manual. So if you cite the pages in your lab manual, that can save you a lot of work finding the spectra that you need. The experimental data that you're going to be analyzing are found in the experiment 28 page on Canvas. And I also posted a recording of a large scale bromination of multiple different amine and amide substrates. And what's nice about the recording is it has some melting point data and it has the mass data for both your reactant and product. So you're going to need to watch the video to fully collect the data on the amount of initial mass of reagents used and the mass of isolated product. Again, you need to watch the video to get the initial mass of reactant used because the amount that we're using for this prep is different than the lab manual. So look at the Canvas page and watch the video to get the amounts of reagents used. Does that make sense to everyone? Perfect. So what we're going to do is we'll archive this recording